Hi everyone. Welcome back to Dave's Math channel. I'm your host David Tare, and this is my second video in a series of 7 videos on the Millennium Prize Problems. I did my first one a couple days ago. That was on the Riemann hypothesis, which is my favorite one of the 7 Millennium Prize Problems. And in case you don't know, the Millennium Prize Problems, these were a set of 7 problems, each with unsolved problems, each with $1 million prize for anybody who can solve them. One of them has already been solved. The Poincaré conjecture that was solved by Gregory Perelman in 2002, but the remaining 6 are still unsolved, and anybody who can solve them gets $1 million prize. And the one I'm going to talk about today is P versus NP. And just to give you an idea what this means, this problem concerns computational complexity. In other words, how difficult it is to solve a particular type of problem. So it's kind of a problem about how difficult it is to solve problems. And the problems we call P, I'll define this in detail later, but P are basically what we call easy problems. Problems that are easy to solve. And examples, shifted and multiplication. You probably learned that in grade school. That turns about to be an easy problem in a way that I'll define. Even Rubik's Cube turns out to be easy in the way I'm going to describe later. But an example of a problem that we don't know if it's easy or not is Sudoku. This is a problem that we call NP. And NP, we don't know if they're easy to solve, but we do know they're easy to check. So I think most of you who've solved a Sudoku puzzle probably know that they can be very, very difficult. I know I have a hard time solving them myself. But, once you've solved them, they're easy to check. I mean, you just check that all the numbers in each row and column and each little square add up to 9, I think. And example of problem that's neither P nor NP is chess. Chess turns out to be difficult to solve. It's difficult to play chess. I think all you guys know that. Yeah, or a perfect game of chess. It's also difficult to check that you've played a perfect game of chess. So that's an example of a problem that's neither P nor NP. It's just difficult all the way around. So that kind of gives you an idea what I'm talking about. And actually, the problem P versus NP, I haven't even said what the problem is yet, but the problem is basically whether P equals NP. And if P equals NP, that means that every NP problem is P. That means that every problem that's easy to check is also easy to solve. And I think most mathematicians believe this is false. It would be kind of disastrous if it turned out to be true because, for instance, cryptography. Every crypto system that anybody comes up with, at least any classical crypto system, the whole point of a crypto system involves a one-way function. It's supposed to be easy to encrypt, but difficult to decrypt. That's the whole point of cryptography. So anyway, but let's begin. So the starting point for studying P versus NP, we have to talk about computational complexity theory. And I'm not going to go into what this slide means, but we have to define terms very precisely what we mean by easy problems, medium problems, hard, and hardest. So anyway, this graph I think is nice. So this is kind of this is what's called big O notation. I don't know how many guys are familiar with this, but if you studied any computational theory, you should know what this means. So it's basically how difficult a problem is in terms of the input size. So just imagine you have a computer program. It's good to think about computer programs because I think every problem in the world you can translate into a computer program, basically. And I think the easiest problems are problems where the running time is constant. It doesn't even depend on the size of the input. I mean, an example of that would be just a simple program where you give it an input like a number and then just output the number you put in. That doesn't take any time at all because all you have to do is read the number and print it out. Print zero. Maybe it does take a little time if the number's really long to print it. But any problem that doesn't disregards the input and just prints some message, some fixed message, obviously that has constant time because it doesn't even care about the input. But those aren't very interesting problems. But then I guess the next easiest are what are called logarithmic time. And logarithms, I think, as you guys know, grow very slowly. So a logarithmic program would be a program where the running time is only proportional to the logarithm of the size of the input. I don't know any particular problems. Like I can't think of them off the top of my head. When we talk about the size of the input, we're really talking about the number of bits in the input. So, for instance, if you had say a 100-digit number, it's easier to think about binaries. So I guess 100 bits. That would have n would be 100 because n is just the input size in bits, and a 30-digit number has about 100 bits, and if your input's a number up to 30 digits, that would be your input size would be 100 bits. So you'd have to have some kind of algorithm that could solve this particular problem in a size that's proportional to the logarithm of the number of bits. That would be very fast, and I can't really think of one off the top of my head. But let's just keep going. Linear is a little bit easier. So it turns out that addition is a good example of a linear algorithm. So imagine you have two binary numbers. It's easier to think about binary. But imagine you're just trying to add two binary numbers, and you add binary numbers the same way you add decimal numbers. You just add column by column and do all the carries. You can do that with bits as well as with decimal digits. And there's like one operation for each column, and the number of columns is just half the total number of bits. So, for instance, you had two, say, n-bit numbers or 200-bit numbers, your total input size would be 200 bits. And then the number of operations, number of additions you have to do is 100. And that's a linear function. It's half of the input size. Um, so that's an example of a linear algorithm. And linear is an example of polynomial, by the way. A linear polynomial is just a polynomial of the form ax plus b. But polynomials, you can have terms that are any arbitrary power. And I guess the next hardest would be, well, then there's also log linear. These are a little harder than linear, n log n. It actually turns out, this is interesting, shift and add multiplication turns out to be n squared, order of n squared. Think about it. I mean, forget about bits. Just think about decimal numbers. It's probably easier to think about decimal numbers. If you're doing shift and add, say you have two numbers you're trying to multiply, each with, say, 10 digits. Well, you're going to have to do 100 shift and add operations, 100 additions. Um, so that's like the square of the number of bits. But it turns out to be not the most efficient way to multiply two numbers. Turns out the most efficient way. There's actually several algorithms, but all the most efficient ways to multiply two large numbers turned out to be O of n log n. Fast Fourier transform is an example of that. I think I talked about that in another video. I'm not going to talk about it in detail, but just suffice it to say there are algorithms for multiplying two large numbers that are much faster than shift and add. They're almost linear. Pretty remarkable, actually. And so linear, quadratic, these are all examples of what are called polynomial time. And then you could have higher degree polynomial n cubed, n to the fourth. As long as it's some constant power of n, we call those all polynomial. Those are called p, by the way. And polynomial time algorithms are called easy. That's the p I was talking about before in this picture. The p on the left means polynomial time. Now you know what it means. And it turns out Rubik's Cube is an example of a polynomial time. There's a polynomial time algorithm to solve Rubik's Cube, any configuration of Rubik's Cube. But then there's harder problems. There's exponential problems. Those problems, the required time to solve them is an exponential function of the number of bits. I guess there's some searching. I mean, just kind of brute force search is an example of that. Suppose you were trying to search for a particular element of an array, sorted array. Well, the best you can do with a classical algorithm is to just kind of, well, it's binary searching, but maybe that wasn't a good example. I don't know. There are other algorithms that are exponential. Maybe searching is an example. Sorting. I don't know. I guess searching through an unordered. That's what I was thinking. Yeah, if you have an unordered array, first you'd have to sort it, and that takes a long time, and then you can search. But I mean, it's simpler just to do a brute force search through a unordered array, or it doesn't have to be a numerical array. It could be an array of names or whatever, and you just kind of have to search one by one until you find the right one. That's an example of an exponential time algorithm. That's very slow. It's very inefficient, but we don't know how to do it any better than that. And an example of the worst possible, I think just about the worst possible, the hardest kind of algorithm we know about is factorial. It turns out the traveling salesman is an example of that. I think I have another slide that shows these. Yeah, and this slide just shows we don't know, we're not just concerned with time. I've been talking about time complexity, but there's also space complexity. So you're not only concerned with how long it takes to perform an algorithm, you're also concerned with how much memory you have to use in your computer to run the program. Obviously, you might have a really fast algorithm, but if it takes up all the memory in your computer, you probably don't want to do it. So we worry about space complexity as well as time complexity. And there's names for all these different things. And one thing I haven't talked about yet, I haven't talked about deterministic and non-deterministic algorithms. Most computer algorithms are deterministic. That just means that there's a program you can write that it always does the same thing when you run it. That's what we mean by deterministic. I think all classical algorithms are deterministic, even ones that involve pseudo-random numbers. But I guess a non-deterministic. I mean, you can think of a non-deterministic algorithm as like rolling dice. There's an element of randomness involved. That's what I mean by non-deterministic. It doesn't always do the same thing given the same input. And so there are algorithms that like NP, the name NP, and you can see it on the slide towards the bottom. P is deterministic. So what P means, an algorithm we call P, if it can be run in polynomial time, the time required to run it is big O of some polynomial of the size of the input n, and we call that P. But that NP, we mean that there's a non-deterministic algorithm that can solve it in polynomial time. But these non-deterministic algorithms are a little bit mysterious. I mean, you might just get lucky. But another way to say that, if there was a non-deterministic algorithm that could solve your problem in polynomial time, you can kind of run it backwards, and then you can see that you can check it in polynomial time. So an equivalent definition of NP is it's a type of problem that there's a deterministic algorithm for checking your result in polynomial time. So the question is whether P equals NP. The question is whether or not if you have a non-deterministic algorithm that can solve your problem in polynomial time, whether or not there's a deterministic algorithm. If P equals NP, then that's true. If not, then there are NP problems that aren't P. And that would be nice for cryptography, for instance, RSA. RSA is known to be NP. It's not known as P. I'll get into that a little bit more later. And I don't think I need to talk about the space complexity, but because it doesn't really pertain to the P versus NP problem. But and then this just kind of gives you some examples. This is just a chart telling you what the different kinds of problems with different types of complexity are, and they give some examples on this slide. And I think the last one I mentioned, the factorial, that's the hardest one. That the traveling salesman's a good example of that. In case you guys aren't familiar with the traveling salesman problem, I might make a video on that at some point. The idea is you have a bunch of cities, a bunch of points on a map. So you have a list of cities. You have a salesman that needs to deliver a product to a bunch of U.S. cities, say, and you want to know what his most efficient route is to go to all those cities. Like what route should he take that minimizes his the total distance he has to travel to get to each city in the map. That is a solvable problem. It's a very, very difficult problem to solve. As a matter of fact, we don't know any method for solving it that's faster than factorial time. That means if you had 100 cities, the time required to solve this problem is like 100 factorial, which is a huge number. So, you can't do that many cities just because the complexity grows so much as you increase the number of cities. Um, but anyway, uh, and then here's just some NP naming conventions. P I already described. That's problems that can be solved in polynomial time. But NP is problems that can be checked in polynomial time. But then there's different types of NP. There's NP hard. Those are the hardest of the NP problems. They are NP, but we don't know if they're P, um, um, and then there's NP complete. I think NP complete. I think if NP complete are known to be NP, but they're not known whether they're P. But any other NP problem, I think, can be translated on NP complete problems. So it's kind of the most difficult class. I'm not an expert on this stuff, but anyway, I just thought I'd show you this. Um, and then, yeah, so now we're sort of getting into the P versus NP problem now. So we have this thing called an Euler diagram, which kind of shows you the relationship between these different types of problems: P, NP, NP complete, and NP hard. And it turns out that the NP complete problems are the problems that are in the intersection of NP and NP hard. So NP complete problems are NP, and they're also NP hard. I guess NP hard aren't NP necessarily. Um, but if P equals NP, then we just all NP complete problems would then be NP. Well, that's already true. All NP complete problems are already NP, but then they'd all be equal. So I guess one way you could test whether P equals NP is you could see whether, and it's enough to check whether every NP complete problem is P. If you could prove that, then you would prove that P equals NP. But there'd still be problems that are NP hard. I guess those are problems that you can't even check in polynomial time. I didn't check the definitions, but anyway. But now I want to talk about some practical applications of the P versus NP problem. I already mentioned cryptography, and right now the most common crypto system that's used, the crypto system that kind of protects all your passwords and all your private information on the web, that's RSA. And in case you guys aren't familiar with RSA, it involves it's what's called a public key crypto system. There's a public key and a private key, and so you have a sender and you have a recipient. I usually call them Alice and Bob. Sender, you start with plain text data, but then you encrypt it with a public key. Then you have ciphered text, but then Bob has a private key he can use to decrypt the plain text, and then he can decode the message in such a way that no eavesdropper can decode it. So it's secure. But the security, the reason I'm mentioning this right now, is that the security of RSA actually relies on the difficulty of factoring large numbers. The way RSA works, I'm not going to go into detail, but it encrypts data using the product. The public key is the product of two large prime numbers, and the reason it's secure is because it's easy to test whether a number is prime, a big number is prime. That was proved recently to be a polynomial algorithm. I think it was the AKS algorithm in 2002 was the first known algorithm for testing primality in polynomial time. So primality testing is known to be P, which is a really nice result. That means you can test whether or not a really big number is prime. But what you can't do is it's much harder to factor the product, a really large number, in particular the product of two prime numbers. So with RSA, usually the way RSA works is you take two really large prime numbers. I think right now they're using primes with about 300 digits. So your public key is a product of two primes, each with about 300 digits. That's about a 600 digit composite number. There's a product of two primes. It turns out that there's no classical algorithm that's known right now that can um, um, factor such a number within the age of the universe. Pretty amazing. I mean, we could do it for maybe up to about 150 digits, I think, right now. I think that's about the limit with the fastest factoring algorithms we know. But we can't do 600 digits within the age of the universe. That's how difficult factoring is. Factoring is not believed to be P, but it can be checked. It is NP. That's what's interesting, and it has to be NP in order for RSA to work, because you have to be able to check that. Actually, it's very easy to check whether a factorization is correct. You just multiply the two numbers together. That you can do obviously in P, because I just said multiplication's P, but it's not known whether it's a polynomial time factoring algorithm. And most people, I think most mathematicians believe there isn't. And if there were, if someone discovered one, then guess what? RSA would be obsolete, because then we'd be able to crack every encrypted message that was encrypted with RSA. There's actually a pretty good movie about this. There's a movie that came out in 1994, which I really like, called Sneakers. I don't know how many of you guys saw that movie, but in that movie, I guess there was a code breaking device that this mathematician, he figured out how to factor large numbers in polynomial time, and he came up with this amazing decrypting device that could decrypt any code in the world, including like the Federal Reserve or the airlines. I mean, theoretically, someone could hack into the airline's website and crash two planes if they wanted to. So it was obviously something that you wouldn't want to happen, and that's kind of the plot of the movie. And we don't know. Maybe something like that could happen. I don't know. But I guess the last thing I want to talk about is quantum computing. And actually, I think this would be a way we could break RSA, because it's already known, by the way. Peter Shor came up with an algorithm. Actually, it was the same year I think the movie Sneakers came out. 1994. There was a computer scientist named Peter Shor who actually discovered a quantum computing algorithm that could factor large numbers in polynomial time. And don't worry about it, because we haven't, quantum computing is still in its infancy. Even though this is a theoretical result, you would need a quantum computer with hundreds of qubits, which we don't have yet. Hundreds of reliable qubits. If we ever had a quantum computer like that, then we could factor large numbers in polynomial time, and we could crack RSA. So I guess Sneakers could happen with a quantum computer, um, I mean, so this kind of adds a new dimension to complexity theory. Now we have another class of problems which we call BQP. This is bounded I guess Q stands for quantum polynomial time, and I guess factoring is an example of a BQP algorithm. And you know, uh, we don't know if it includes all NP problems. That's why they don't show it overlapping all NP. But it does add a new dimension to the P versus NP problem. But I guess QP quantum algorithms aren't really part of the P versus NP problem. This is all classical. But anyway, so that completes my video for tonight. That's my, I'm not an expert on this, like I said, but I kind of gave you the basics of what P versus NP is about, and why it's important, and why I think most mathematicians want it to be false. P is not equal to NP, but maybe it is. We could solve it either way, and I think there is a $1 million prize if you can prove that P equals NP, or if you can prove that P is not equal to NP. I think whoever is offering the Millennium Prize problem is just as happy with either result. And I'd be pretty impressed myself if either result was proven. Anyway, that concludes my video for tonight. Thank you for watching. Long live math, and I'll see you guys next time.